Hello, I'm Frederick Cho, and I'll be presenting my joint work with Matt Weinberg on the communication complexity of VCG-based combinatorial auctions. Let's start with the problem setting. In a combinatorial auction, we have m items and n bidders with private valuations, which go from sets of items to non-negative reals. The welfare is just the sum of the bidders' valuations, and the mechanism is a communication protocol amongst the bidders and auctioneer, which outputs an allocation of items to bidders, along with prices that each bidder pays for their share of the items. Our goal is to design a mechanism that gets three things. First, we want it to output an allocation with good welfare, which we'll quantify later. We also want it to be efficient with regard to some resource utilization, like computation or communication, for example. Finally, we want the mechanism to incentivize bidders to follow the protocol, a property called truthfulness. Formally, we want truthful behavior to be an ex post Nash, and intuitively, we're saying that the bidders want to maximize their welfare minus their payment, and we want to design a mechanism where no single bidder can obtain better utility by deviating from the protocol. Another part of the problem setting is the valuation class we're considering. In the general problem, we'll allow the valuations to be any monotone function, but this can make good approximations very difficult because arbitrary monotone functions can be really complex. Maybe we're interested in a mechanism that doesn't handle those cases well, but is much better in more practical cases, so to speak. So often we'll restrict the valuations to have some kind of structure. On top of the general case of arbitrary monotone valuations, the classes of valuations we'll mention in this talk are subadditive, XOS, and submodular, which all capture a slightly different notion of diminishing returns, with submodular functions being a subset of XOS functions, which are a subset of subadditive functions. We'll mention these classes throughout the talk, but the actual definitions I put here aren't too important. With all that background out of the way, we can talk about the big question, which most people agree is important, and that is, can truthful mechanisms, which must incentivize bidders to follow the protocol, be as good as their algorithmic counterparts, which assume bidders follow the protocol? To properly talk about this, we'll need to quantify what we mean by good welfare and efficient mechanisms. The measure of welfare we'll be using is the approximation ratio, where a mechanism is alpha approximate for some alpha greater than 1 if it always outputs an allocation whose welfare is within a factor of alpha from the optimal welfare. And the measure of efficiency we'll use is the communication complexity, which is the number of bits we need to send to run the protocol for the mechanism. Why not use another model, like computation or value queries? Consider the example of the demand query, where we show the bidder a price for each item, then ask them for their favorite set of items at these prices. It's not unreasonable to expect the bidder to be able to answer a demand query because they intrinsically know some facts about their own preferences. But computing a demand query is actually NP hard. So in other words, the communication model is attractive because there are natural ways to communicate which are formally hard to compute. This talk is about VCG-based mechanisms, which are also called maximal and range mechanisms. MIR mechanisms are pretty much the only way we know how to design deterministic truthful mechanisms for combinatorial auctions, so we're interested in figuring out exactly how good they can be. One thing to note is that we do know better randomized truthful mechanisms than their deterministic counterparts, but also note that the guarantees of randomized mechanisms are in expectation, so we might get bad welfare with non-negligible probability. We can't amplify the success probability with repetitions either, because repeating a truthful mechanism doesn't always preserve truthfulness. So there are definitely good reasons to be interested in deterministic truthful mechanisms. So what is an MIR mechanism? The classical VCG mechanism says that if you have a welfare maximizer, then you can use it as a black box to generate prices which will incentivize truthful behavior. The problem is that maximizing the welfare takes exponential communication. Now, suppose that instead of considering the space of all possible allocations, we consider just a subset of the allocations, which we'll call an allocation bank. Some examples might be the set of all allocations, which gives all the items to one bidder, or the set of all allocations, which gives one item to each bidder. It turns out that if we have a welfare maximizer over any allocation bank, then the VCG mechanism can turn this welfare maximizer into a truthful mechanism as well. The key idea then is to carefully choose an allocation bank, which is simple enough to optimize over efficiently, but complex enough to still contain good allocations for any set of bidders. Our results improve both upper and lower bounds for the approximation ratios of MIR mechanisms for all ranges of communication, where we have a parameter k and allow the mechanism to use 2 to the k communication. For general evaluations, we close the gap between the bounds from root k log m to a constant, which resolves the communication complexity of MIR mechanisms for general evaluations. For submodular, XOS, and subadditive evaluations, we close the gap between the bounds from polynomial in k and m to root log m, which is near optimal but leaves room for future work. And this is what the results look like if we let k equal log m, which is the polynomial communication case. Due to time constraints, I won't be going over any proofs in depth, but I will sketch out a unifying framework for the upper and lower bounds of general evaluations, and I'll also give some intuition for how we improve the lower bounds for some modular evaluations. So, general evaluations. The framework we'll use for general evaluations is an analog of shattering from the concept of VC dimension. So just as a refresher, we say that a collection of sets curly f shatters a set S if restricting curly f to S results in the power set of S. So in other words, any configuration of the items in S is included in curly f. Now, in our case, we don't have collections of sets where an item is in the set or out of the set. We have allocation banks where an item goes to one of the n bidders. So to directly extend the concept of VC dimension from collections of sets to collections of allocations, we can say that an allocation bank, curly A, full shatters S if restricting curly A to S results in the full set of allocations. So in other words, curly A can arbitrarily assign items in S among the bidders. We'll also say that curly A full shatters S between bidders T if curly A can arbitrarily assign items in S among bidders in T. And finally, we'll say that an allocation bank, curly A, 2 shatters S if there exist pairs of bidders for each item in S so that curly A can arbitrarily assign items in S between those pairs of bidders. So you can think of this like full shattering, but instead of each item being able to go to any of the n bidders, each item can only go between a specified pair of bidders, which could be different for each item. And we won't need shattering for now until we get to the submodular lower bound, but listed here for completeness. So this generalization of shattering is interesting because it pretty much exactly characterizes MIR mechanisms for general evaluations. And what do I mean by this? Well, on the welfare side, we can show that if an allocation bank full shatters every set of size k, then it is M over k approximate. And as sort of a converse, if an allocation bank is M over k approximate, then it full shatters some set of size k between a pair of bidders. So there's some kind of equivalence between full shattering sets of size k and being M over k approximate. And for some intuition on why this equivalence exists, you can basically think of it as if we want an M over k approximation, then we need to get the k most important items to the right bidders. And full shattering every set of size k lets us do that. On the communication side, we can show that there exists an allocation bank which full shatters every set of size k and takes 2 to the k communication to optimize over. And again, as sort of a converse, if an allocation bank full shatters some set of size k between a pair of bidders, it requires 2 to the k communication to optimize over. So we have another kind of equivalence between full shattering sets of size k and taking 2 to the k communication to optimize over. And now if we chain together the first statements in each pair, then we get that there exists an allocation bank, which is M over k approximate, and takes 2 to the k communication to optimize over. And then chaining the second statements in each pair together, we get that if an allocation bank is M over k approximate, then it requires 2 to the k communication to optimize over. And That pair of statements together exactly resolves the communication complexity of MIR mechanisms for general evaluations. And the cool thing about this framework is that it was already used in prior lower bounds, so our improvements there were just refinements in the analysis. But no prior work tried applying this framework to the upper bound as well. And doing that is what gave us the insights we needed to design an optimal mechanism. Great. So now we can move on to lower bounds for submodular evaluations. So here's the definition of two-shattering again for reference. And just for comparison to our approach, I'm going to sketch how the prior best lower bound goes. So we'll fix the number of bidders to be the cube root of m over k. And a previous result shows that if an MIR mechanism is cube root m over k approximate with some hidden log factors for additive valuations, which is a subset of submodular XOS subadditive valuations, then there exists a two-shattered set of size m over n. And now, just remember that each two-shattered item goes between a pair of bidders. So since there are only n squared pairs of bidders, some pair of bidders has m divided by n cubed, which is k, items full shattered between them. And then from there, since submodular evaluations are pretty rich, we can pretty much use the same communication lower bound as for general evaluations to conclude that we need 2 to the k communication to optimize. Now let's look at this argument a little more closely. A helpful interpretation is to think of two-shattering as a graph, where the bidders are vertices and the items are edges going between the corresponding pair of bidders. Then wherever there are edges, we can basically think of it as bidders need to communicate with each other to figure out who's going to get which items. And so what the previous argument narrows down to is that if we have a lot of items two-shattered, then there is a pair of bidders with k parallel edges, which requires 2 to the k communication to resolve. But this is wasting too much in some sense, because it's ignoring pretty much all of the items and bidders. So instead what we found is that the right notion of difficulty of communication to consider is the presence of large cuts in the two-shattering graph. And so if you think about it, large cuts pretty much indicates that there is some large number of items that are in contention between the bidders, and they're going to need to do a lot of communication to figure that out. So let's try this argument again, and this time we'll set n as root m over k. Then by the same result as before, if an MIR mechanism is root m over k divided by root log m approximate, there exists a two-shattered set of size root m times k. And now what we'll note is that since there are k times as many edges as vertices in the graph, that means that we can find a subgraph where every cut has at least k edges going across it. And we actually need a slightly stronger result that has to do with multi-way cuts, but the details that I've written here aren't too important. And then, if you recall, edges kind of represent these dependencies between bidders where they have a hard communication game to solve. Since every cut has at least k edges across it, we can pretty much take this structure and embed a very similar hard communication game for XOS valuations. And if we want to go all the way to a submodular lower bound, then we have to do quite a bit more work, and that has to do with the communication game itself, which I won't have time to get into here. So that was a brief excursion into the submodular lower bound. And one thing that I want to highlight is that unlike our type bounds for general evaluations, there is a root log m gap between our submodular upper and lower bounds. And we have constructed examples that show it's impossible to improve the lower bound using the same kind of two-shattering argument that we used. And not only that, but every known MIR mechanism can be implemented with simultaneous value queries. And we also show that any MIR mechanism which uses either value queries or uses a simultaneous protocol cannot beat our MIR mechanisms. So in terms of future work, there is a small open question to resolve this root log m gap. Although what's really of interest here, though, is less closing the gap itself but seeing what new approaches would allow the gap to be closed. Because, as I said on the previous slide, pretty much we've reached the limits with the approaches that we've used. And aside from that, there is still the big open question, which is, can we get similar results for deterministic truthful mechanisms in general? So we can conjecture that MIR mechanisms are the best we can do deterministically, and there's some evidence to suggest that. And if that's the case, then our work almost resolves the matter. But there's very, very little progress in proving or disproving this conjecture. So solving that would be really amazing. And that concludes my talk on the communication complexity of VCG-based combinatorial auctions. Thanks for listening.